Well, yeah, you don't want to hear all
Testing
that
one,
extra
two,
noise.
three. Excited.
Because what I think we
We are on
decided
location.
this
What's up? What's up? What's up, everybody? We are live on location. Welcome once again to Building Stuff with Nova. Listen, you all see the Nova t-shirt? You know what that means, right? Today I have my superpowers, and we're going to take it to a whole new level today because as you can see, I don't know if you can hear very well, but as you can see, I'm not in the normal place. This whole week we've been doing a lot of things different, but I need to get a quick check. Can you understand me as I tell you once again? Put a 1 in the chat if you can hear me very clearly that this is your virtual makerspace, your ideation laboratory. This is the mastermind where you and me and everybody in the chat, we see you both on YouTube and on Twitch, we can build together. So I'm super excited today because I am at Vanderbilt University and I'm standing right next to someone who's going to guide us on a virtual field trip. Tell people, what's your name?
Yep, I'm Christina McGann. I work at Vanderbilt in the clean room, a room that is really clean.
The room that is really clean. We're going to tell you exactly why that's important in just a moment. But this is called the VINCE, right?
Yes, the Institute of Nanoscale Science and Engineering at Vanderbilt.
Vanderbilt Institute of Science and
Nanoscale Science and Engineering.
Science and Engineering. That's what VINCE stands for. So when you hear me say VINCE, I'm not talking about my homie. Shout out to Vince. But I'm talking about this lab, all right? So here's the thing, right? Before we get going, I got to remind you, as we always do, we want to hear from you here on the channel. So I'm going to give a shout out to Nova. As a matter of fact, I think Nova's in the room with me right now. Then we're going to drop some links in the chat. Shout out to Nova. That is Angelica. And we have Stephanie behind the camera. We want to hear from you all. So in the chat, we're going to drop a link so you can, one, complete a survey. But also, we are looking for signups for people to participate in a Zoom interview. And guess what? For that one, we actually have an incentive, $100. $100 gift card for those of you who sign up to be a part of the Zoom interview. We don't just want your feedback in the survey, but you have the opportunity to do that and talk to us in person. So look out for the links. Shout out to Nova, dropping it on both YouTube and on Twitch. This is your opportunity to be a part, all right? That sound dope? All right. So if you're excited about today, here's what I need you to do. I need you to drop some emojis, drop some fire in the chat, drop some love. We need some energy right now because I have my superpowers with me, but I'm going to have to suit up even more, right, Christina?
Yes, indeed.
All right. I got to stay clean. I'm partially clean right now, but now I got to get, like, extra clean.
Indeed, we have to protect the clean room from all of us, our hair, our skin cells.
Uh-huh.
We can't have that.
You can't have that?
Can't have that.
All right. So tell me, what am I going to put on right now? We have, like, a whole...
We got a whole assortment of things we're gonna put on.
Okay.
So we're gonna put on a hood.
A hood, okay. Let me see. My hood is right here. Here's my hood.
Perfect.
All right. Shout out to Angelica. Angelica, you mind holding this mic for me as I put my hood up?
Hi guys.
Put your hood up. Here we go. All right, so I'm putting my hood on, Christina.
Perfect.
Make sure I'm doing it right, because this
exactly.
is like the Iron Man helmet kind of thing, right?
You snap in the front.
Snap in the front. Okay, cool. I'm ready, y'all.
All right, we have a mirror over there, but you're doing challenge
I can see
mode.
myself in chat. Chat, I see myself in you. We're one at this point. We are one at this point, and if you see yourself in me and you're ready to go, that's not cool. Ouch. All right, so helmet. What's next? Like I gotta put on
All right,
shoes.
so we got to put on the full clean room science coveralls. The whole armor, indeed.
All right, so this is what I've already put on though is gloves and shoe covers, but now I'm covering that even more. This is like extra layers, right?
Exactly, because our clothing fibers will actually shed tiny bits of fiber that are large compared to the size of the tiny things we're making in the clean room for science.
Got it. And is this made out of a certain material?
It is. It is a specific fiber combination that will not shed.
Okay.
And that we can still launder regularly.
Because there's going to be a lot that we're going to learn about, like how, as you said, cleanliness goes down to the microscopic nanoscale, even
smaller.
So
exactly.
Smaller than we're dealing with stuff that's smaller than what you can see on the microscope. That's crazy. Nanoscale. All right.
Yes, indeed.
So
all right.
next.
We got to protect our eyeballs.
Eyeballs?
So we got to put on glasses.
I need my eyeballs for sure.
They help. All right. We look very anonymous, so we got to put on a name tag.
All right. So we need to be able to know the difference between Christina and me. So I know we look exactly the same right now. So here's my, so this right here, Christina.
Perfect.
All right. What else I need?
All right.
What else?
Last thing we got to do, boots.
Boots. All right.
So the easy way, if you don't want a major balance challenge, is you sit down, put on a boot, swing your leg around.
I was a little nervous. I was about to try standing up.
Yeah.
But I don't want to fall because this is live. And if I have a blooper like that, Christina, I don't think chat will ever forget it. They'll be able to watch it. As a matter of fact, what'd you say?
They'd be like, I don't know, man.
Yes.
No concussions on live streaming.
None of that.
We don't need that today.
Shout out to Nova. Now, I don't know if y'all know, but this is the person right here that's holding the microphone that whenever I say, Nova, can you drop that in the chat? Is that you, Angelica, who drops it in the chat?
That's me.
Yes.
Hi, guys.
So can y'all say, hey, Nova / Angelica?
Unsnap here.
Hey, everyone. Nice to see you in the flesh this time.
Perfect.
All right, cool. So this, next one.
Indeed.
I need some love from Angelica. Drop in the chat. Thank you so much for all the facts that you would share. I just want to say publicly
The Opal guy says hi.
For-
Opal, Angelica, and Stephanie.
for making sure that, whenever I talk about bridges or anything else, that we back it up with actual facts. So that's the person, you all. Show some love. We've gotten y'all to see the whole team throughout the course of the series. And now we want to see a lot of people that are on Christina's team, right, Christina?
Yes, indeed. We'll be seeing some of our graduate students who work in our clean room, as well as some of our staff who help keep the clean room clean and teach people how to do everything from putting down material and taking it away and making really cool patterns to make everything from the computer chips in your phones to better ways to grow cancer tumors so that we can treat them better.
Wow. Sounds like world-changing activity.
We try.
And now I'm ready to go. Am I good?
You are good.
All right. Make sure you all hit follow. Make sure you all go ahead and if you are on Twitch for the first time, you haven't hit the follow button.
So it says take the little, did you turn it off?
No, I think yeah. Testing 1, 2, 3.
Put it like, I put it in where like.
Put it on the collar.
Okay.
Angelica.
Can we hear? Angelica, help me out. Angelica. Nova, can you help me out really quick? Nova is helping me mic up. This goes on the inside. All right,
Tricky
cool.
with gloves, huh?
Yeah, tricky with gloves. All right, we're good to go.
Finish zipping up.
Yep.
Zipping up, snapping.
Let me know in the chat. I know we're getting I know you're getting dizzy right now, but let me know if you can hear me. If you can hear me, then we're good to go. We're good to go, Christina. Thumbs up. Thanks, Nova, AKA Angelica.
Yep, I think we're good.
All right,
Excellent.
let's make it happen. Oh, well, I've never been here before. I'm a
right.
superhero that's nervous right now.
So if you fist bump the motion sensor,
Boom.
you can enter.
Open.
It's thinking about it.
Okay. And this right here I'm walking on is like a sticky.
It is. So it's kind of get all that extra dirt off of your shoes.
Last minute dirt. Okay.
Exactly. We gotta be as clean as humanly possible.
Oh man, I see a bunch of clones in here.
So yes, clearly have a bunch of clones. These are engineering and science students in their natural habitat.
Hello everyone. We come in peace. We come in peace. All right. So what are we gonna see first, Christina?
Yeah. So first we're gonna hear a little bit about how, besides our outfits, we actually keep the clean room clean enough that we can do our science. Where the scale of a human hair, the thickness of it is large. So we got to filter out all of that.
Okay.
So we're gonna hear a little about from our clean room manager, Ben,
Okay.
who will tell us about how HEPA filters and furnace filters are only the start of what we do in here.
The beginning. Okay.
Exactly.
All right. Hey, what's going on, lab manager? How you doing?
Good, how's it going?
Nice little clean fist bump. I'm good. Thanks for having us.
Thank you, we're excited you guys are here.
Okay, cool.
Let's see.
All right, we're switching the mic here.
Okay.
Are we good in the camera? All right.
Well, my name is Ben Schmidt. I'm the clean room manager here at Vince. Welcome.
Thank you.
Glad to show you all around what we can do here. Just a little bit of background. I have a bachelor's and PhD in chemical engineering. I actually got my PhD here at Vanderbilt a few years ago.
Hey.
And so I've been working here in the clean room for the last few years. And so just wanted to talk to you about how we make this place so clean and why we need it to be so clean.
All right.
So to start about, you may have heard from Christina already, who uses clean rooms? If you're building things for semiconductors, computer chips, maybe lenses for microscopes or telescopes, maybe pharmaceuticals or medical devices, it's all very important to make sure we don't have little bits of dust, because you can imagine if you're in the middle of playing a game and a dust particle short-circuited your chip, and it crashes, you're going to be pretty upset.
Yeah.
Or if we had a telescope halfway across the solar system and there's a tiny bit of dust making that image a little bit blurry, we're all going to be very disappointed. So whenever we make those things, we want to work in a clean environment like this.
And even the smallest piece of dust can disrupt how it operates, and it could, I guess, disrupt really the manufacturing of it as well.
Exactly.
Okay.
Exactly.
Got it.
So how do we make this place work?
Okay.
So what I'm going to show first is my nice display box.
Okay.
You can see it's full of air. And this is 1 cubic foot of air.
Really?
Now, if we took this cubic foot of air outside, we have all kinds of particles floating around. We have dust and pollen and things coming off our clothes and our skin.
Mm-hmm.
You know, how many particles do you think you could imagine might be in that airspace?
A lot.
Lots.
Yeah.
What are we thinking? Millions, maybe?
Yeah, millions, because like we're talking about things we can't see.
Exactly.
Yeah. Okay.
So when we come in here, as Christina mentioned, we are filtering the heck out of this air, and we are in that same airspace, especially this part of the room, that number drops down to less than 1,000. When we get down to a different part of the lab, that number drops down to less than 100.
Yeah.
And so what we're trying to, again, avoid is making sure that any dust is floating around cannot land on the things that we're trying to build.
Right.
And so we can do that with filtration. So if we look up overhead, we can see that there's holes in the ceiling.
All these are filters?
These are all this is all filtered air coming right down on top of us. This is
all the way across.
Some of the cleanest air in Middle Tennessee is what we're breathing right now. So if you have allergies, this is a great place to work.
This is a great place to, okay. And I noticed too that when you're talking about the filtering process, chat, you all didn't see this, but we went through, that room we were just in was already one room. So it's like a progressive process.
Exactly.
We got clean, we go in that room, we get cleaner, I stood up, and then we come in here and you're telling me now the particles are less than 1,000, but we're gonna go to another place where you continually make it, I guess, cleaner and cleaner.
Exactly,
All
exactly.
Right, let's go.
And we have filters for this. This is an example. This is a HEPA filter, which is up above the ceiling. And so we have both this type of filter and also the filter you may see at your house, like the furnace filters, kind of the cardboard kind of fabric. We start with those, and then we go the HEPA filters. So again, we're using that all through this area that you see above you is the nice filtered air.
Okay.
And so it comes down from the ceiling,
yeah,
and it's pushed out through these grates in the floor. And
now, so these are the vents here, filter and vent. And
exactly.
You're right, this is a lot, because I guess in your typical house, these are like every so often placed.
Right.
But you have like the number of them because of the high volume in which you need to filter
We're
air.
continuously rotating it and filtering it over and over again.
Over and over again.
And so, you know, we think about, okay, so that's a good way to filter the air that's in here, but how do we prevent particles from coming in? And how do we deal with them once they're in here? So we have a couple other things I wanted to show. So what kind of things can we bring in the clean room? You know, a lot of researchers are doing, you know, they want to take notes. Can you bring in just your standard sort of lab notebook with paper? Of course not, because if you think about tearing that, that's going to generate all kind of dust.
Microfibers of
of
the pulp and everything in the air from the paper.
And so we have very special notebooks that have a special type of paper that will not produce those particles.
Are you serious? Clean room notebook.
Exactly. We have, what do you think you would use to write down your
pen.
notes?
That's a regular pen though, right?
Regular pen. Is it a clicky pen?
No.
Can we use a clicky pen, do you think?
Because every time you click.
Exactly. Every time you click, it's going to generate
Chat,
particles.
I had no idea, like particles everywhere. Man, so they can't use clicky pens, can't use normal paper. Yeah, and then what is this right here?
This is, so if we have, let's say, some particles or dust got on this table, we can use these. These are kind of wipes that we can use to wipe it. And again, these are special textile materials that will not generate lint and fibers so that we can keep it clean.
Yeah. Wow.
So, and then we also have to do our chores, just like everyone at home. We have to do our vacuuming.
Vacuum, okay.
We even get this guy, which is like a giant lint roller. Have you ever had to use this on your clothes to get the lint off?
Actually, do they sell those? I have a few suits. I haven't.
You get one of these guys.
Oh, wow.
That'll really get the dust off the floor and the walls.
It's sticky, y'all. It's sticky. So.
Oh, yeah.
It's a lot of, yeah. No dent, no lint. So this is a special vacuum too?
Exactly. It has a HEPA filter, the same type of filter we use in the ceiling. So it's a very high efficiently collection filter. And we use this to collect all these very small particles so we can get down to the very small particle counts that we need for the research.
Got you. Now chat, listen, you probably already have questions and we're gonna get to it. Just go ahead and drop them in the chat for now. And later on, when we get a moment, we'll pause and take some of your questions. Again, shout out to people who are on YouTube or on Twitch right now. We're going to get to your questions a little later. Just drop them in there, and we'll have the team. Shout out Angelica, Kajo, everybody behind the scenes. We'll try to collect them later to ask our experts here. All right.
All right. I think I'm going to take that mic.
Okay, great.
All right. Thank you, Ben. Y'all give a shout out to Ben. Say thank you, Ben. Appreciate it. Nice little clean fist bump. All right. We're going to let you get back to your chores. You got chores to do. All right.
That's right. Got to get back to work.
Excellent.
All right, Christina, that's really just fascinating because we haven't even gotten to like the science. There's the science behind making sure that it's clean. So we haven't even gotten to like the science of what's happening, what needs to be clean.
Exactly. This is the reason why some of IBM's clean rooms that are only 10 particles in that foot, they only have robots. People are just too dirty. Like no matter how clean you are not clean enough.
So you're saying there's a level to this. This is the academic environment. You got students, we saw them earlier. And then the industry environment where they're actually creating and shipping these chips that go into our computers and telescopes, lenses and stuff like that. They have an even higher standard. And so they don't even use people. They just use robots.
They do.
Robots taking our jobs. They're too clean. All right, here you go.
So yeah, what we have to do is, or what we are able to do in academic clean rooms is we're basically more flexible in what we'll let people bring into the lab. So we can do, in addition to semiconductor chip processing, we can do things like making custom wells to basically grow cancer cells in, or special tiny pipes that mimic what goes on inside of our organs.
Oh, okay. So you're talking about like little things that help facilitate other parts in our body or biological material,
exactly.
right? And so you want to make sure those are clean so that they don't interact with whatever you're having in your body or the cells that you're trying to grow.
Exactly.
Okay,
they're called organs on a chip.
Organs on a chip. Has a ring to it. All right. Organs on a chip. All right, so I see here, before we even go in, some extremely tinted windows. I see yellow. This is like orange. It's all like very tinted. Does that have anything to do with the cleanliness?
Not as much the cleanliness as the third thing we'll do in the clean room, that's making patterns.
Okay.
So a lot of how we pattern is with ultraviolet light, so blues, purples. We have these light-sensitive liquid plastics, but we also have very nice windows that have the sunlight that have blue light in them.
So, all right, so the sun, that's intentional too, the big
is.
windows. Okay, so the sun comes in. What does that do exactly?
It is helpful for morale.
Okay, keep your spirits up as we are saving the world from the itty bitty germs and unclean particles. I love it.
Exactly. So we can't have any of that blue and ultraviolet light in here. So if you take a look at your glove now, what color is it?
Bluish purple.
Bluish purple.
Yeah, y'all see that?
Want to fist bump that motion sensor?
Fist bump, nice little clean fist bump.
Excellent. So let's head in. Once this door closes, you can tell me what color your gloves are.
We are now in the yellow room. It's like washed out kind of. I don't know, chat. What color do you think this is? Gray.
It's gray.
Gray. Wow. Did I change colors too? No, I'm just playing. All right. All right. So what we got here?
So yeah, this means we've effectively blocked out all of our blue and ultraviolet so that we can pattern things.
Okay. So the light, the ultraviolet and blue light in here can somehow disrupt the patterning.
Exactly.
Okay. All right. So let me make sure I understand this. Chat. Make sure we're together because I'm trying to make sure I follow this too. I'm a structural engineer, not a microparticle nano cleanliness engineer. So here's the thing. You need to pattern things on these small chips and stuff.
Yep.
And whatever device you use, because I assume we're going to see what the device is.
We are.
All right, cool. Whatever the device is, if it has the wrong light spectrum in this room, it gets disrupted through the patterning, in the patterning process.
Exactly.
Okay.
We have a light-sensitive liquid plastic.
Okay.
So we want to pattern with the blue or ultraviolet light where we want to pattern and not where the sun wants us to pattern.
Oh, the CERN. Yeah, okay, got you.
But again, morale.
Morale, we need the morale out there, and then here, we don't need none of that morale. We're down to
Precisely.
business. Okay, all right, so what do we have in here in terms of equipment?
So in here we got some ways to coat that liquid plastic onto our sample.
Okay.
So that we can actually transfer patterns in. We have a convenient grad student who does a lot of this patterning himself.
Okay, how you doing? I'm doing well. Clean fist bump. Owen.
Yes.
All right, I'm Dr. Nee. This is the building committee. We call this channel Building Stuff with Nova, and we are now live on YouTube. Shout out to the YouTube fam. Make sure you hit subscribe if you haven't. And we are on Twitch. You know about Twitch?
Of course.
All right, so this is not your normal Twitch content. Like, we're not just playing games.
Yeah.
I mean, we're not
We're
just
learning.
We're learning. And which, by the way, let me just plug this again. We want to hear from you all. Again, in the chat, you may have seen Nova drop our Nightbot on Twitch, a survey where we want to hear your experience with this informal engineering activity, education. This is a part of a research project supported by the National Science Foundation, and we need to know how you all have experienced this. And it's not only through a survey, so everybody, whether you are a new viewer or you've been coming regularly, we need to hear you, and we want you to fill out the survey. But if you want to take it a step further and get on a Zoom interview, we have $100. That's right, Christina. $100, a $100 gift card for people who will sign up for Zoom interviews. So as Nova drops that in the chat, we're going to look for you all to sign up so we can get the feedback, because we like to do this stuff. I like to come in and meet people like Owen, who are about to break down for us exactly how this patterning takes place inside of this clean room.
Yeah, of course. So I'm Owen. I'm a third-year graduate student here. Okay. I work on teeny tiny electronics, but before I can work on them, I have to make them. And before I can make them, I need to pattern them.
Okay.
And so, like we've mentioned, this is all blocked out from the UV light, except for right here. We have a big source of UV light right in this black box right here. And so what we're able to do is we're able to shine the light forward and onto a sample that we can put right here.
So what you're saying is, we blocked out, Christina told us we're blocking out the UV light, and that's so that you can control it precisely in the patterning process.
Exactly.
Okay, so what type of sample goes there?
Yeah, so right here we have something called a silicon wafer. So silicon is an element made of sand. And so this is very pure, very flat. And then we've put a light-sensitive chemical on top. So if you see, it's very thin, so you can see it change in color as you look at different angles. But what you can do is you can put this right in here. And then
you put the little wafer in the spot where we're gonna control our UV laser. Is it a laser technically?
It's just a big lamp. So it's a mercury lamp. We heat up mercury really hot, and it shoots out.
Is this called
UV light.
So is this called what is it? Is it not a sputtering system?
No, this is
ELB or something like that?
Oh, you'll get to the EBL next.
Oh, EBL. Okay, cool.
This is a mask liner. So this is a mask. So if you're thinking we're shining a light down onto our sample, we don't want it everywhere. We want a pattern.
Yeah.
So we have this chromium mask where the chrome will block the UV light from getting through. So some places will get a lot of UV light onto it, and other places will get no UV light onto it.
Got you. So it's like a stencil for the light.
Yes.
All
and
right.
the benefit of this is that you can do a lot of patterns really fast. You can do one pattern. You could do millions of little shapes all in one exposure.
Well, how can you do millions if you need a mask in a sample? Like,
So there'll be millions of patterns on that mask.
Oh, okay. So
you can cut up the chip afterwards.
Yeah. So then you can go later and cut it up and get a bunch of different samples out of it.
got you. So this is creating the mask.
This is the mask.
Oh, that is the
And
mask, but I
it's
mean, like,
creating the pattern from the mask.
pattern from the mask. Yeah,
Yes.
yeah. Okay, got you.
Okay, so what we've done now is we brought them together, and so they're really close to each other, actually touching. And what that's going to do is that's going to give us the smallest resolution that we can get. We can get down to about 50th the size of a hair.
Wow.
On this patterning. Can we go smaller in here? Yes, but you'll have to wait to see how we do that later.
Okay. But the 50th the size of a hair, that's already
That's
pretty
already
small.
really small.
Crazy
yes.
small. Okay. Especially my hair.
Yeah.
I'm bald headed. That's right. Good. All right.
Okay. And I think we're ready. We're ready to go ahead and shine the UV light down onto the sample and see what happens. So I'm going to go ahead and hit the exposure button, and you're going to see a big mirror come forward and start to shine down. And so this is like shining the sun straight at this, and it's going to expose for just a few seconds.
Mm-hmm.
And that's it.
So it already created or used the mask to shine the light now into the pattern that we need.
So now, this was one plastic all over, but now we've created two different plastics. All the places that were hit by light, those long chains of polymers that make up the plastic, are chopped up into tiny little chains.
Yeah.
And so in a second, we'll pull it out, and you'll see there's really no difference. It looks just about the same.
It looks exactly the same.
But what we can do now, just like a picture, we can take it over to a chemical, and we can develop the image on it.
Oh, kind of like when we had to develop photos.
Exactly.
In a solution, are you going to drop it in like a liquid?
Yep.
Okay.
So we're going to go right back over here to these containers that I've set out.
What kind of liquid is this?
So this is a very basic solution, so not the opposite of an acid.
Yeah, basic.
Not simple.
The equipment we just used is a mask aligner.
Mask aligner, okay.
Mask
Yes.
to a sample.
Yes.
So that was a mask aligner. All right, that's the name. Thank you, Christina,
Yes.
for telling that. Mask aligner. By the way, Nova, if you're in the chat, go ahead and drop some factoids about the mask aligner as we get ready to look at this basic, I don't know why I use air quotes, but literally basic fluid. Okay.
And so I put on another pair of gloves because, as Christina mentioned, this suit is to protect the environment from us. Now I'm protecting myself from the chemical.
Okay.
So what I'm going to do is I'm just going to take the sample.
You got a little pair of like whippers there.
Little pair of tweezers to pick it up.
All right.
And I'm going to drop it in.
Let's
And
develop
we'll see
that.
instantly starts changing colors, and that pattern comes out.
Chat, that's dope. Y'all gotta drop some fire. I need to see some flames in the chat for that. That is dope. So now it's coming. Now, did it already have what it needs to operate, or this also it allows us to see it, but does it also allow it to operate?
Yes, so now we've exposed that bare silicon underneath, so we can continue to do more processing on it.
Or okay.
So you can see, right there we have a nice pattern. And so the really nice thing about this mask aligner is it's very versatile. We can use this to make tiny little pipes to imitate the body and like how our body works. Or we can make tiny little electrodes.
Okay, that's the part that I'm missing though.
Yeah.
Maybe you can help me out, Owen. That's not a tiny wafer. So how do you use this big thing here to create something tiny?
Yeah, so it's kind of hard to see on this one, but if we'll open up one of my samples right here,
Okay.
you can see there's a lot of little dots right here.
Yeah.
And all over there, I've deposited metals, and like you'll see later on, there's lots of different things, processes that go after patterning. Because now you can put down metals, or you can etch. And so each one of these dots is a tiny little electric device
Yeah.
that you can barely see here, but once you look at it under a microscope or something, there's lots of
circuitry, basically.
exactly.
Maybe we need to put that in our escape room. I don't know. But if you all don't know, we're doing a finale that's going to be a 4-part escape room, Christina, Owen. And it's going to be right here with you all. And we're going to be doing electrical circuits and everything. You all make sure you're there because we need to solve this. But what they're doing here is basically making electrical circuits as small as they can possibly be made on little chips.
Yes.
That's amazing. All right, fun fact, maybe Nova can drop this in the chat, but Silicon Valley, as we call it out in California, is connected to, it got its name from the material used to make these chips, right?
Yep.
All right, there's some fun fact. Let's fact check me though, because I probably said it a little weird, but shout out to Nova in the chat. Shout out to Angelica, who would normally be the person doing that. All right, what do we got next? Owen, are we going back to Christina?
I'm going back to Christina.
Yeah, going back to Christina. I am going to take this mic back from you.
Yes.
Hopefully I didn't just turn it off. We'll
All
find
right.
out.
Owen, thank you so much.
Of course.
All right, stay clean.
Actually,
Stay clean, my friend.
you know what? While we're here,
We're going this way? Okay.
just for a tiny bit. So we showed how we can use masks. We can also make our own masks. So if you look here, you can open it up. You
Open
can
this
see.
up.
Yep.
Okay.
So this is a stencil that we'll use to make
Mask.
electrical contacts.
Okay.
So for solar cells. and we can basically write that in a liquid sensitive plastic using this laser writer. It writes the pattern with a laser. It's very creatively named.
Yep.
And we're basically turning off, there's a laser in here that turns on and off really quick as we pattern. And we're basically going slice by slice so that we can create all of our own stencils to use, as you saw how quickly Owen can do his patterning.
So use that to create the stencil or the mask that you then come over here, use the UV light to write the pattern that you need, come over here to
Exactly.
Owen in our basic fluid, not special, basic fluid, and then we develop it, and then from there, we're able to then move forward to create chips? Is that the
Exactly.
name?
Yeah, we can create electrical devices, devices to make better VR headsets that are not like this thick,
Yeah.
and everything in between.
Okay, now, before we leave the room, I want to know, chat, if you had any questions. Do we have any questions we can bring up? Shout out to Nova, aka Angelica, over here checking the chat. If there are any questions, we're going to see if we can ask while we're in this room. But one of the things that I think is amazing as I wait for questions is I've heard you all throw out tons of applications already.
Oh, yeah.
Out there, you all are talking about computer chips. You were talking about telescope lenses when we were talking to Ben. And then I hear you over here talking about like solar cells. Like, there are tons of applications for the things you all do here.
Yes, it's super fun. We even have some geologists coming in to dice up their really special, unique rocks into like teeny tiny cubes so that they can like image them with an electron microscope.
Wow.
So we do a little bit of everything.
A little bit of everything. Okay. Do we have any question we can quickly ask while we're here? We are live on both YouTube and Twitch, so we want to get at least a question in. Shout out to the team that's remote as well.
Can we talk a little bit about how often those air filters need to be replaced?
Ooh, good question.
Yes.
The question was, how often do the air filters need to be replaced? You got an answer?
Yes, I do.
Okay.
So the like cardboard paper filters that are more like what are in your furnace, we replace those every 2 years. But the big ones, those are actually good for like 7 years.
Wow.
So we're due for one of those in a few years'
In a
time.
few years. Sounds like a good business. I might need to start clean room air filter business in addition to hosting live streams. All right, what else we got as far as questions?
Question about whether dead skin cells that fall off your face, if that ever becomes like
Dead skin cells. So like right now, we can still see a little of my face. And I got some thick eyebrows too. So what if my eyebrow dandruff, dead skin cells fall off? Does that?
So yes, that could be a problem.
Okay.
Before we used to wear masks in the clean room, I imaged one of my samples that I had taken like a whole week to make, and there was like a little spiky virus particle on it.
Oh my goodness.
I was very displeased about that, but the picture was cool.
The picture was, it was a cool picture of something that wasn't supposed to be there.
Indeed.
All right, got you.
That's why we work in these hoods that have basically airflow that is going
It's
this away.
continually filtering even more.
Exactly. So we try to keep ourselves as much away from our samples as we can.
Got you.
Do you want a shoe adjustment?
I think we're good. I think we're
All
good.
right,
Yeah,
all
yeah.
right.
Do we have one more question before we move to another location?
One more question. People were curious if you make any of those cleaning tools in-house, like
Do-
the roller.
Sadly, we have not. We
Okay.
don't have a. I guess our macro scale makerspace. We probably could make some custom tools.
That was a question about the tools that we saw out there. So that just sounds like, chat, another business we need to start. Air filters, clean room tools, and educational live streams. All right, sounds good. What's
Excellent.
next?
So what's next is we talked a little bit about how we can make patterns with light, which are pretty darn small. You can fist bump.
Yeah, I got you.
Excellent.
My
Blue
power.
is suddenly a thing.
I've definitely, when trying to defer doesn't work. You're the host. I should have walked through this door first. All right, anyway.
That's okay. We got it. So we're going to find out how we can make patterns even smaller.
Okay.
Because basically, light is limited by its wavelength. That is how big that is. But that's like only 50 times smaller than a human hair. But what if we want to make smaller stuff?
Even smaller, nanoscale. By the way,
Nanoscale.
and maybe chat, if y'all can do this, give me your example or your analogy of a nanoscale. I want to know, how do you all describe that? Because 50 times smaller than the hair is not nano?
No, that's still
So
micro.
that's not nano? Okay.
It's big nano.
It's big nano. All right, give me an example of what nano is. In chat, we'd love to see you all's your representations in the chat too. But what would you say?
So stuff like red blood spells are getting pretty small, but you have to go about 1,000 times smaller than the thickness of a single human hair for some of the nanoscale stuff we make.
1,000th of a hair. So we're talking about smaller than red blood cells.
We're pretty small.
So this stuff isn't even visible on a microscope.
Not a light-based microscope.
Got it.
Not at all. So we're going to use something that's even smaller than light, which is electrons.
This is crazy. All right,
So we
even
got like
smaller
a-
than light.
oh, yeah,
All
we
right,
got a
so
whole
what is this
special
called?
room
We're going
for
into
it.
another like tinted room, right?
We are. So both of these tinted rooms are lithography bays, that is patterning areas.
Okay.
So we have a whole special room inside of here. Yep, we can fist bump.
Go ahead, fist bump. This is the
And-
only
yeah.
power I've been using.
Oh
the whole
yes,
time.
we
All right.
definitely have the fist bump motion sensor power.
Okay,
That's a
all right.
critical one. So what
So
we got in
lithography.
here? So lithography is
No
patterning.
way. Can you drop the I guess the textbook definition as Christina tells us in layman's terms? Lithography is
Yeah, lithography is patterning stuff.
okay.
Came
Pattern.
from like historical lithographs
Gotcha.
and like wood carvings and stuff, if I recall correctly.
Oh, that's dope.
But
Okay.
now we're going to pattern with electrons.
Electrons. All right. Which
So-
is you have to control the electrons some kind of way.
We do. We
and
got
you're
magnets.
directing the electrons. So this equipment, this expensive equipment, I got a feeling that it's pretty costly.
Yeah, a little bit.
Controls how you are able to channel and precisely write things with the electrons.
Yeah, that's exactly it.
All right, cool.
So we have a whole special room for that purpose.
Oh, another room. Okay.
So you can see this door is very thick. If you kind of check an angle here, you can see all of the damping
Mm-hmm.
to damp all of the vibrations. So this includes, you walking around, construction going on, even cell signal.
Mm-hmm.
I can start a call out here, and if I go in this room and close the door, my call will drop.
Instantly. Okay, cool. So if I ever want to have a secret conversation, I
You're
can
good.
Go here. Okay.
You go in an EBL room, an electron beam lithography room.
Got it. And it look like you have another grad student in there.
We do.
Okay.
We have Theodore, who's going to tell us a little bit about the electron beam lithography he's been doing and brag about some of his cool stuff that he's
All
been
right,
making.
Cool. He can't hear us right now, though, right?
He
'Cause
cannot. He cannot.
All right.
So he doesn't know.
He doesn't know. Okay.
I mean, he does know. But
Oh,
he doesn't
yeah,
know
all
we're imminent.
Let's ambush.
Yes.
Theodore. Oh,
So
push.
it's a very heavy door. So it will
Everything
feel
here is
wrong
fancy, y'all.
either way. Yes, there we go. That one's not a motion sensor. Sorry to disappoint. All right, so
Everything here is so fancy. Push door. Hey, how's it going? I think Theodore has something to share with us. Now, Theodore, as you were getting mic'd up, I want you to know that I've already been beyond impressed with the fact that you all can go down to 1,000th, do something at 1,000th the size of a hair through, what is it, e-beam, I saw on the door.
Electron beam lithography.
Electron beam lithography. All right, break it down for us.
All right, so just a brief introduction. I'm
Yeah.
Theodore Anyika. I'm a fourth-year PhD student here, and today I'm going to be talking to you about the electron beam lithography tool we have here in the Vince Clean Room. So, like you previously discussed with Owen, we could actually make patterns that are like a fifth of the size of the human hair, a 50th of the size of the
50th,
human hair with like photolithography. However, when it comes to like spatial resolution, you can only go so small with light.
Yes.
It has wavelengths, and wavelengths are kind of like large, but the way to actually get really small, as small as like 1,000th the time of the human hair, the size of the human hair, is to significantly shrink the size of the wavelength. So there is, quantum physics. I'm sure a lot of people have heard about that.
Yeah, of course.
But
I read that
with-
this morning.
Yeah, with quantum physics, you can actually describe particles like electrons in terms of waves.
Yes.
So they have a wavelength. So the wavelength of electrons is around like 100 to 1,000, the wavelength of visible light or ultraviolet light that we
Right,
actually use for
right.
patterning. So what that basically tells you is that you can go really, really small, and in some special kind of electron microscopes, you can actually look at individual atoms.
Wow.
So it's really mind-boggling, right? That's really, really tiny. So the trick here is to actually emit electrons using some kind of electron gun. There are different kinds of it.
Yeah.
And then you focus this electron beam with a magnetic lens, and then you focus it right onto the sample. However, one major difference between this and the photolithography system is we have to work on a very high vacuum for this.
Very high what?
Vacuum.
Vacuum, okay.
Yeah, it has
okay.
to be done completely in vacuum, right? So you can think about it this way. Imagine you're trying to kick a ball across the room,
Okay.
and you have a goalpost, and you have a lot of people in the room.
Yeah.
There is a very high probability that your ball is going to bounce off of someone.
Somebody, yeah.
So it's a very similar kind of scenario. So if you have like molecules and gases and particles in a chamber, if you shoot your electron beams,
It's
they
going to
could-
bounce. Someone's going to block
Exactly.
my shot.
Exactly.
Okay,
So
got you.
basically, you wouldn't really get the kind of resolution that you need.
Right.
So we have to work on a very high vacuum
And move all the people out of the way and all
Exactly,
the particles.
exactly.
And let me have a clear shot.
Exactly. We want a clear
Becky.
shot from the gun to the sample.
Okay.
So
all
there
right.
is this thing called the load lock,
Okay.
and there is something called the main chamber. So we load our sample through the load lock.
Load lock. All
So
right.
the way it works is we like or we prefer to keep the main chamber always under high vacuum.
Okay.
So the way it works is you have a valve that separates the main chamber from the load lock. If we
Okay.
want to load our sample in, we have this valve closed. This is on a high vacuum. We pump this down, or we vent it, so we kind of pump air in it to atmospheric pressure. We open it, we load our sample in, then we pump this down, that's pump air out of it, and then it's back onto vacuum. And then we can open this valve when both of them are under vacuum. So
Got it.
that way we always maintain this guy on a high vacuum, and part of the reason is it takes a while to pump this guy down.
Yeah.
So this is a lot faster.
So here's the thing. There are two things that come to mind from an engineer perspective when it comes to this thing. If you're going to turn it into a vacuum, it needs to be sturdy enough material that it doesn't like collapse upon itself.
Yeah.
So that's why this is made out of like metal, heavy metal, right?
Yeah, correct.
It's a heavy thing. All right, cool. So that's one thing. And the other thing is, and maybe you're going to get to this. In my mind, I see some sort of nozzle that's shooting out electrons. Like, how do you control the electrons? And more so, like, what is the fuel? Like, where are you getting? Like, obviously, you can't go and pick electrons.
Yeah.
Like, what's happening here for us to make sure that
So-
only electrons come out of whatever this nozzle is that's writing?
Yeah, so there are different ways that you can like shoot out electrons.
Okay.
One is through something called, one way is that you can heat up a material and it shoots electrons.
So heat it up.
That's
Okay.
one way. That's not how we do it
That's
here.
not how we
Another
do it here,
way is
okay.
you could apply an electric field, and
Okay.
it basically strips off electrons off of the material. Now, one thing I would like to point out is if you have a charged particle,
Mm-hmm.
if it moves in a magnetic field, you can precisely control the motion. So there is a lens,
Mm-hmm.
but it's a magnetic lens. Electrons are negatively charged particles, so
Yep.
we can precisely control the motion of like this beam of
By
electrons.
moving the opposite charge and basically pulling it around, in a sense?
Not necessarily. It's not that simple.
Okay.
It's a little bit more complicated than that.
All right.
But,
But it's almost like plasma. It reminds me of plasma in a sense. Like you create a
Yeah.
magnetic field.
yeah,
and then you,
it's-
okay.
There is some good similarities.
All right,
but
you know,
the way to think
shout out
about
to
this is,
MIT.
if you look at like regular microscopes, you have light going through an objective lens. You can focus your light to a spot.
Yes.
There is something called a magnetic lens. You can focus a beam of electrons to a spot.
To a specific spot.
Yeah, so now the fact that the wavelength is really small means that you can focus to a really small spot. And that is how we get to like around 1,000th the size of the human hair.
Amazing. Amazing. Y'all gotta drop some love in the chat. I know we have questions continuing to come, and by all means, we'll try to get to them a little bit. Theo, I don't know if you have anything to show us, but if
Yeah.
not, we do have questions. What do you got?
Yeah, so well, I could like quickly show you a sample, one of my samples.
This is the software that is
Yeah,
allowing you
yeah.
to take a look at the samples?
Yeah,
Okay.
so this is like the main tool, and all of the engineering and physics goes on in there. And this
Okay.
is like the software part of everything.
The software part. Okay.
Yeah, so what you're looking at right now is a scanning electron image of a sample that I made previously, kind of like a long time ago, right? So it's an
Okay.
old sample. But what you're seeing here are gold pillars on a gold film. So, right? So I'm pretty sure one thing you're wondering is like, why am I making this?
Yeah, I mean
Yeah.
gold. I mean, does it have to be? I mean, gold is interesting.
Well-
by the way, okay, go ahead.
Oh yeah, well, gold for reasons because gold doesn't really react.
Oh, okay.
So in my lab, we like to use materials that are not very reactive.
Got you.
And specifically, what I'm trying to do with this is to actually trap very small particles. So I'm trying to trap like really small particles, like 100 nanometer in size. You can think of this like maybe on the scale of like individual viruses. Yeah, so we can actually hold them in place, right? So we call it nano tweezers actually. The way you use like tweezers to like pick up like really small objects that you can use your hand. If you want to like hold individual like viruses or some biological particles that we call exosomes, which we are very interested in, these are like really small.
Yeah.
We can use these kind of chips.
I see. That's exactly what I was thinking. So the chips are really picking.
Exactly. That's
they're
exactly
nano
what it's doing.
tweezers,
They
like,
are literally
as I would do with
nano
my.
tweezers.
Got it. Okay.
Yeah, so the way it works is when I like illuminate this with light, you can have like a force generated around this nanoparticle, and that force can actually hold very small objects.
Gotcha.
And then we can, like study these objects and figure out their properties and different kind of things.
Yeah. Are they doing what we need them to do at that nano scale?
Yeah, exactly.
Okay. Yeah, we need to make sure. All right, so let's see. Do we have any questions we can quickly get in while we're in this awesome E-beam lithography room with my man Theo, who just broke it down. I helped out a little bit, I think.
Yeah.
Okay, all right. Yeah, I kind of helped out. All right. Any question?
Sure, we had a question about whether, like, being in rooms of this color, like, do you have to do any sort of, like, detox afterwards? You get used to it?
Yeah. Like, this is light. I don't know. Does it kind of somehow mess you up a little bit?
That's a pretty good question. I think typically you just get used to it.
You get used to
pretty
it?
much.
All right.
Yeah. One thing you're going to notice is, like, when you finally step out of here, the sunlight looks a little bluer for some reason.
Bluer, yeah.
So it's kind of like your body like adjusting to the different environments.
Yeah.
So you get used to it.
It's a brain thing.
Yeah.
Get used to it. Just like you probably got used to this high-level science that we're all being introduced to for the first time on this
Yeah,
screen.
pretty much.
All right, cool. Well, y'all show some love to Theo. Anything else? Yeah, we get. Oh, you got one more?
Sure. I mean, people are very interested in, like, the decontamination protocols. So just
Okay, maybe Christina, when we slide out, Christina, we're gonna get you back with the mic, but we want to know more about the protocol. Chat, as we're switching the mics, I do want to again remind you all that we have a finale, a 4-part finale happening starting October 27th. Go ahead and fact check me, Nova. We're gonna be having a 4-part engineering themed escape room where you're going to, in chat, help our participants in real life solve problems related to all types of engineering: structural, mechanical, electrical, energy, the environment, aerospace. And it's going to be an interactive experience. I'm going to go to Boston. We've already selected our crew, and we are going to, as in the game, save the world from all the hazards of Y3K. So mark your calendars for that. Nova dropped the reminder of the date. As I step out here into this blue room, I mean, whoa, you're right. Theo knew exactly what he was talking about. It's blue in here. But anyway, I hope that you all will join us for the finale because it will be the opposite of blue. It won't be sad. It'll be very exciting. All right, Christina, protocol about like everything. People were asking more about like scheduling and protocol.
ask a specific question if you want. Just like
Yep.
if there's any sort of alarm system.
Is there an alarm system like dirt?
There is. We
Okay.
actually have what are called particle counters that are in every single of our rooms. And if the particle count gets too high, all of the fans that are controlling the air that comes down whir up to like 100% speed.
Yeah.
And just like are trying to flush everything out really quick. So we got alarms for that. We got
Yeah.
alarms for, sometimes we use gases that will light on fire.
Get out of here. And so the fire is purifying?
So
Or-
they light on fire if they meet with air,
Oh.
specifically oxygen. So we have like alarms for if any of those things are not where they're supposed to be.
That is kind of scary.
It
but
is.
I'm glad you have alarms. All right.
Yes, we have stuff like that. We got hydrogen, that lights on fire with the Hindenburg. We don't need that in
We
our
don't
lab.
need that, yeah.
But sometimes we need it to make materials that are a single atom thick. So we got
Gotcha.
lots of alarms and safety protocols
Right,
for
right.
dust and for other nasty things.
Nasty things in case it gets out of hand. All right, that's really cool.
Exactly.
That's really cool. All right, what else we got? I'm having a blast, by the way.
I'm
This
glad.
is
I'm
awesome.
glad.
Yeah.
So yeah, here we got Megan, who's going to tell us a little
Hey.
bit about etching.
Clean bump.
Hello.
Hello, we got Megan. We're going to get
Mic-
Megan
gonna
mic'd
mic
up.
Megan.
Hi, everybody.
Megan, this is the building committee. We are live on Building Stuff with Nova on Twitch and YouTube.
Hello.
Say hello to Megan. Drop some emotes. Drop some fire. I just got a feeling just from standing this close to her that she is brilliant. And we're going to find out what she knows here right now.
Yeah. Hi, everybody. I'm Megan Dernberger. I'm a staff engineer here in the Vince clean room. And right now we're standing in what we call the etching bay. Etching is the removal of material. We have two different types of etching. We have some wet etch, which would be using a liquid chemical, often acids, or a dry etch, which is using plasma, which is energized gas, and you'll see it as a glowing color. You'll actually see that in a little bit.
Awesome.
We actually have two examples here. I don't know if you can see that, but we have some spirals. Our silicon, which is this darker color, was dry etched with a plasma, and our glass, which is this lighter color, was etched with an acid.
Wet etch.
Wet etched with an acid. And these are about 25, 30 microns deep, which is pretty deep.
Yeah.
And then we have a few other examples that we can go very complex with our different patterning, which you saw earlier, our lithography, and have really small pillars. Our diameter is less than a micron, and we're about 7 microns deep.
So those pillars are representative to how deep you're etching?
Yes, this is some silicon, and you can see that there's pillars. They're all silicon. The tall columns, that is what's left, and then the trenches is the material removed while etching.
So you can almost think of like the etching. First of all, it looks artistic.
Yes,
It's like someone just kind of got their little art on, but you can think of them almost as like grooves that allow other things to flow.
Yeah, these examples were different optics. We can control how light interacts at the very, very small scale with these different pillars. And you'll see a few things combined at our next station with Grace and deposition, which is laying down our materials.
Got you. Told you she was brilliant. I told you, I could just feel it. So really quickly though, back to the fact that it feels like artwork almost, because I see spirals. Is there something in the shape, or do you get freestyle with it? Like what determines whether you do a spiral or you do something else?
So these spirals are for particle trapping. So we can have a particle go around our spirals, and also what we call microfluidics, really tiny pipes that we can put different cells inside and control how they flow.
Gotcha.
So the design is based on what you want it to do.
What you want it to do. So when you say a particle trapping, is it because you want it to go down but not make it all the way down to the...
Yeah, the different sizes can then separate it out, and it can go all the way.
Gotcha.
They interact differently.
I see, and so yeah, it kind of filters out, and I can see why you don't want a small dust particle.
Yes.
Because it'll kind of like just block the way.
Yes.
And now we've etched this entire thing, and even though it looks cool, it doesn't work.
Exactly. We need it nice and clean.
You need it nice and clean. So fresh and so clean. All right. What is, are we, so you got anything else for us?
No, that's all for me.
Okay, all right. Give it up for Megan in the chat. Make some noise. Burr, 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 in the chat for Megan. Megan, thank you for your time. Really appreciate it.
And yeah, some of those artistic lenses with the different cylinders are actually used to do edge detection for image analysis using actual optical lenses as opposed to doing it with computers, so that we can save some of the computer resources for the harder parts, say for like computer vision in autonomous cars.
Okay. So you're saving some of, you're being efficient with your resources there.
Precisely.
Gotcha. All right, so we're over here around some more impressive equipment for sure, and we got Grace.
We do. We got Grace who's going to tell us about how we actually put down some materials and some of her cool science.
Give it up for Grace coming to the stage in the clean room. It's Grace Adams.
Hi.
Can I get a clean fist bump?
Yeah.
All right, cool. Introduce yourself to Building Stuff with Nova.
Hi, I'm Grace. I'm a second-year PhD student in biomedical engineering.
Also, biomedical engineering, and you're doing something that's also pretty brilliant back here. I can just tell.
Yeah, so this is our sputter deposition system. So this is how we deposit a metal onto, or any material onto another material. And we use a state of matter called plasma, which is made up of positive ions.
Oh, okay. I was getting warm when I talked about plasma earlier. Okay,
yeah.
all right.
So basically we have a material that we want to coat, which we call a target. And then we have our substrate, which is the sample that we want to coat.
Okay.
And we have a voltage gun, and all of those are encased in this big vacuum chamber. The vacuum chamber is filled with an inert gas called argon or other inert gases. And
What do you mean by inert?
So that means that it's not reactive with the material that we want to deposit.
Something like that. Okay, gotcha.
Yeah. So it's all in a vacuum, so that's the only gas that's in there. And so that we can control parameters like the pressure and things like that for our deposition. So if you look in here, you can see that there's a purple glow in the bottom right, and that's the plasma. So it's glowing purple because of the energy of those ions, and underneath that is a target. Right now I'm sputtering platinum, but this is what a target will look like. This is copper. So it's really just like a hockey puck of material. And so to create a plasma, this voltage gun creates an electric field inside of the chamber, and that moves around the atoms in the argon, and as they collide with each other, the electrons get knocked off and they become these positive ions. And then once they are positive ions in this plasma, the target here is negatively charged because of the voltage gun, and the negative charge of the target attracts the positive ions in the plasma at such a high speed that they slam into the target and they knock off particles of the target, and those particles will fall off and hit the substrate that we want to coat. And as this is happening, it's rotating, so it gets a super thin uniform layer.
Okay. All right, I'm gonna try to, I think I got it. That's pretty awesome. First of all, you use the term coating and you use the term sputtering. They're basically, the sputtering is the process of how you're coating.
Yes.
All right, so sputtering is taking place. But instead of coating it by like in a paint, if you were painting, you would just paint right on the thing you're trying to coat. But because this is so small, nanoscale, you're basically slamming it into something else. So that the particles come off of that thing that it's slammed into, and then that then coats what you're looking to coat.
Yes, exactly.
And it's giving it a, for lack of a better word, super thin layer.
Super thin.
Super duper thin.
Yes.
Super duper duper thin.
Yes.
I will be technically correct. Super duper duper
Exactly.
duper thin. All right, cool. We got it.
This, the platinum is being deposited at a rate of 2.6 nanometers per minute.
Wow.
And so to put that in perspective, a sheet of paper is about 100,000 nanometers. And so if I wanted to deposit the thickness of a sheet of paper, it would take over 600 hours for me to deposit that. But my depositions are only 200 nanometers, so it's only about an hour.
It's only about an hour.
Yeah.
Angelica, did we get any attempts to describe a nanometer in the chat? Electrons. Okay, shout out. We got a lot of intelligent folks in our community, and so in other words, you fit right in, Grace. Thank you so much. And so you said it takes about an hour.
Yes.
And so you do this. Okay.
I get a 200 nanometer layer because I'm making electrodes. These are flexible neural probes that I'll be implanting in mice to record their brain activity. So once I pull my sample out of here, it looks it's completely covered in platinum, and then I put it in a chemical that removes all of the extra photoresist from the photolithography step that you saw earlier. And then I get something that looks like this. And so all of these channels are their own electrodes, and the electrodes are 30 microns in diameter, and that's about the size of a neuron. And so that's why we're able to record at such a small scale, is using these tools like this.
My mind is blown right now. You're trying to get the size of a neuron.
Yes.
Because ultimately, you're going to put this in the brains of mice to be able to determine the activity.
Yes.
So you're producing things on that scale so that you can detect and interact with neurons inside the brain of a mice. That's so small that is blowing my mind right now. That's crazy. Thank y'all so much. Thank you, Grace. By the way, this is incredible. I think at this point, I'm really interested in what you all are doing in terms of nanotechnology. And I've heard so much about plasma, Christina. Chat, we might be plasma scientists by the end of this stream. I don't know, but thank you so much. Was there anything else that you're gonna show? Because right there on as she's taking the mic from you, what you have right there is like a little chip there too.
So once I finish this, the liftoff process, and I have my pattern, I can go through the etching process, which you also saw earlier, and all of my deposition is on a super thin polymer. It's kind of like plastic wrap. And so I'll etch to kind of cut out the shape of each probe. And then I get something like this, which I can attach to a circuit board. And this is how we get the activity from the neurons into a computer for analysis.
Crazy, crazy. All right, we're gonna try to focus it just a little bit for you really quick. Steph is over there doing her thing. As you saw her doing on Wednesday night in the escape room. Go watch that if you all didn't on Twitch. But thank you, Steph, for getting a good shot of that. And Grace, I just have to, because you know, now that I'm a nanotechnologist, it's not just super thin, it's super duper thin.
Yes,
just want to make sure.
thin.
All right, super duper thin.
Exactly.
Thank you so much for your time. I appreciate it. Thank you, Christina. I hope you have, you know, much success on all that you're producing, and you get what you need from those mice.
Yes.
Because you know that can be tricky.
Yes.
All right.
I know.
Cool.
Excellent. Ooh.
Uh-oh. So, Christina, this has been amazing. I don't know if I can even really grasp not just the science that goes into keeping it clean, the science behind the actual things that you're manufacturing in here, but also the science behind the applications that the things you're manufacturing here are going to be applied to. That being said, is there anything you can kind of leave us with as we kind of like look to move forward in this stream?
Sure. Yeah, so we've talked to some of the graduate students who do their research here. Mm-hmm. We also have undergraduate students who work in the lab. We had some who were growing single atom thick materials last week. Mm-hmm. And we have classes in here. We do high school outreach.
Yeah.
So we'd love for y'all to come work with us, check us out, and check out some of the neat science we're doing and be a part of it in the future.
What inspires you really quick? It's because people probably are really interested in this after this tour. What inspires Christina? Because I understand you got your PhD from Vanderbilt, then you came back to where you now work at Vanderbilt. What is it that motivates you? And maybe that can be something that they can hold on.
Sure, yeah, for me it was, you know, starting off when I was 12 or 13, just being really interested in how things worked on a teeny tiny scale and really wanting to get my hands around experiments and tinker and make stuff. And I tried out a lot of different sciences, and nanoscience just seemed really cool, so I kept doing it.
It is absolutely cool indeed. And you know what's also cool, as I let you all know, that next week, we're going to pull up our program schedule. Next week, we have another week of cool program just like this. As a matter of fact, I'm telling you, on Monday, you do not want to miss. You can see it on the screen, but we have a guest by the name of Mick that's going to be joining us, and we're going to be talking a little bit about, you know, you see it, UFOs. So there's also a film that we will be able to hopefully share clips of it from NOVA. You all know NOVA does a lot of cool things. So make sure you join us next week. We're going to be back to our normal times next week. We're not going to do the late night that we did all this week, but 1 p.m. Eastern, 12 p.m. Central, because we are in Nashville, 12 p.m. Central. But with that being said, I hope you all make sure you join us next week on Building Stuff with NOVA. I want to say thank you so much, Christina. Thank you for the time. Thank you for introducing me to all your amazing staff, the lab coordinators, lab managers. I think the applications of the things that you're doing here will literally change the world. So ultimately, these superhero suits actually do fit the part.
And they're really comfy.
And they're really comfy. All right, y'all. With that being said, go ahead and wave goodbye to the camera. Say goodbye to Christina. Give it up for Vanderbilt. The Vince. I want to say again a shout out to Stephanie behind the camera making it happen. Shout out to Nova, aka Angelica, on the ones and twos. The ones and twos meaning Twitch and YouTube. And with that being said, I hope you all take care, and I hope you learned something today. And until Monday, when we come to you with another stream, everybody, anybody, everywhere, make sure you keep building. Peace.